Dear students, I am Hiba Haq, lecturer of physics from Government Degree College, Malir, Cantt, Karachi. In this lecture, I will explain thermal expansion, which is the topic from chapter 11, Intermediate Synth textbook. Uh, let's start. Okay, I have divided my lecture into 5 portions. In first portion, I will explain what is thermal expansion, and after that I will explain what is thermal expansion of solids, which include linear expansion, area expansion, and volume expansion. And after that I will drive the relationship between coefficient of linear expansion and volume expansion, which is beta is equals to 3 alpha. And after that I will drive the relationship between coefficient of linear expansion and area expansion, which is gamma is equals to 2 alpha. And at the end I will explain bimetallic thermostat. So let's start with thermal expansion. The increase in linear dimensions of a solid, or the increase in volume of a fluid. By fluid we mean liquid and gases on heating is known as thermal expansion. If we talk about expansion of solids, when a solid is heated, its molecules vibrate more energetically against the action of intermolecular forces, producing greater displacement. As the average distance between molecules increase, the size of the solid increases. And if we talk about expansion of fluid, when a fluid is heated, the average kinetic energy of the molecules of the fluid increases. So if the average kinetic energy increases, it means the velocity with which they are vibrating is increased. Due to larger velocity, molecules start pushing their neighboring molecules. The average distance among the molecule increase, the volume of a fluid increases. So thermal expansion of solids. The types of thermal expansion of solids are linear expansion, area expansion, and volume expansion. If we talk about linear expansion, it is a one-dimensional expansion. That is the change in length, width, or thickness of a solid on heating. So to understand it further, I assume a uniform thin metallic rod whose original length is L0, and it is at some initial temperature T0. When this rod is heated through a certain temperature T, the length of a rod increases. So let it is increased by delta L, which is equal to L minus L0. So let's suppose this is the rod whose initial length is L0, and it is at temperature T0, and when it is heated to temperature T, which is equal to T0 plus delta T, where delta T is the change in temperature, the length of a rod increases to delta L, which is equal to L minus L0. So you can see it in this figure more clearly, that when the rod is heated, the length of a rod is increased. So now what we do, we try to find out that this change in length depends upon which factors. Okay, so the increase in length or a change in length of the rod depends on the original length of the rod. Experimentally, it is found that the change in length of the rod is directly proportional to its original length. Mathematically, delta L is proportional to L naught. I mark it as equation number 1. And increase in length of the rod depends on the rise of temperature of the rod. It has also been found that increase in length of the rod is directly proportional to the rise of temperature. Mathematically, delta L is proportional to L naught. I mark it as equation number 2. So if we combine equation 1 and 2, we get delta L is proportional to L naught delta T. So by removing the sign of proportionality and introducing a constant alpha, we get delta L is equal to alpha L naught delta T. I mark it as equation number 3. So this constant alpha is the coefficient of linear expansion. If we define it, it is the fractional change in length per Kelvin rise in temperature, or we can say that change in length per unit original length per Kelvin rise in temperature. So the formula of alpha is delta L upon L naught delta T, and this delta L upon L naught is known as fractional change in length. The coefficient of linear expansion is measured in per Kelvin, and it depends upon the nature of the material only. So the equation 3, in equation 3 we know that delta L, change in length, is equal to L minus L naught, that is final length minus initial length. So if we rewrite equation number 3, L minus L naught will be equal to alpha L naught delta T, or L will be equal to L naught plus alpha L naught delta T. We can take common L naught common in this equation. The final expression will be equal to L is equals to L naught 1 plus alpha delta T. This is the expression for the final length of a rod, and which is equal to initial length of a rod into 1 plus linear coefficient or coefficient of linear expansion into change in temperature. Okay, so the second type of thermal expansion of solid is area expansion, and it is the two-dimensional expansion of solid, that is the change in two linear dimensions of solid on heating. To understand area expansion, I suppose a uniform metallic rectangular plate whose initial area or original area is A naught, and it is at initial temperature T. When it is heated through a certain temperature T prime, the area of the plate increases by delta A, which is equal to A minus A naught, where A is the final area of the plate and A naught is the initial area. So this is the diagram in which if the temperature of plate is increases by T plus delta T, the length of the plate increases to L plus delta A, and width of the plate increases to V plus delta V. And we know that delta A is equal to delta L into delta W, and A naught is equal to L into W. Okay, the increase in area of a rectangular plate depends on the original area of a plate. Mathematical experimentally, it is found that the change in area of a plate is directly proportional to its original area, to the original area of a plate. Mathematically, delta L is proportional to A naught. I mark it as equation number 4. And increase in area of a rectangular plate depends on the rise of temperature of the plate. It has also been found that increase in area of a plate is directly proportional to the rise of temperature, or mathematically delta A is proportional to delta T. I mark it as equation 5. So now if we combine equation 4 and 5, we get delta A is proportional to A naught delta T. By removing the sign of proportionality and introducing a constant gamma in above equation, we get delta A is equal to gamma A naught delta T. I mark it as equation number 6. So this gamma is the coefficient of area expansion, and it is defined as the fractional change in area per Kelvin rise in temperature, or we can say that change in area per unit original area per Kelvin rise in temperature. The formula of area expansion is delta A upon A naught delta T, and in this formula, or in this expression, delta A upon A naught is the fractional change in area. So the unit of area is meter square, so this meter square will cancel. The unit in which we measure coefficient of area expansion is per Kelvin, and it also depends on the material, nature of the material. Now in equation 4 we know that delta A is equals to A minus A naught. So A minus A naught will be equal to gamma A naught delta T, or we can say that A is equals to A naught plus gamma A naught delta T, and final expression will be A is equals to A naught 1 plus gamma delta T. So this expression is actually the final area of a rectangular plate, and it is equal to initial area or original area of a rectangular plate into 1 plus gamma coefficient of area expansion into change in temperature or rise in temperature. Okay, now for volume expansion. So volume expansion is actually the three-dimensional expansion of solid. It is the change in length, width and thickness of a solid on heating. So to understand volume expansion, I suppose a cube of original volume V naught. It is at some initial temperature T naught. When it is heated at certain temperature T, let delta V be the increase in volume, which is equal to V minus V naught, where V is the final volume and V naught is the initial volume. So in this diagram, the cube that is drawn by dotted line shows the initial volume, and this cube shows the final volume, which is equal to V naught plus delta V. And this diagram just shows the motion of molecule due to heating a substance. So this the temperature of this cube is T naught, and you can easily see that the motion of a molecule is normal. So when the temperature of a cube increases, molecules start vibrating with larger amplitude, causing the increase in all three dimensions of solid. Now if we talk about the factors that depends on the increase in volume, we have original volume of a cube. Experimentally it is found that change in volume of a cube is directly proportional to its original volume. Mathematically we can say that delta V is proportional to V naught. I mark it as equation number 7. And it is also found that increase in volume of a cube depends on the rise of temperature of a cube. So it has also been found that increase in volume of a cube is directly proportional to the rise of temperature. Mathematically delta V is proportional to delta T. I mark it as equation number 8. Now after combining these two equations, we get delta V is proportional to V naught delta T, and by removing this constant we introduce by removing this proportional sign, we introduce a constant beta, and delta V is equal to beta V naught delta T. I mark it as equation number 9. Beta is coefficient of volume expansion, and it is defined as the fractional change in volume per Kelvin rise in temperature, or we can say that change in volume per unit original volume per Kelvin rise in temperature. The formula for volume expansion is delta V upon V naught delta T, and the unit SI unit of volume is meter cube. So this meter cube will cancel. The unit of coefficient of volume expansion is per Kelvin, and it only depends on the nature of the material. So in this expression, delta V upon V naught is the fractional change in volume. Now we know that delta V is V minus V naught, so equation number 9 will become V minus V naught is equals to beta V naught delta T, or we can say that V is equals to V naught plus beta V naught delta T. So the final expression for the final volume of a cube will be V is equals to V naught 1 plus beta delta T. Okay, now I will derive the relationship between coefficient of linear expansion and volume expansion, that is beta is equals to 3 alpha. So for that, in order to obtain the relationship between coefficient of linear expansion and coefficient of volume expansion, we consider a cube of dimension L naught, H naught and W naught. The original volume of a cube at temperature T naught will be V naught is equals to L naught into H naught into W naught. I mark it as equation number 10. So if this cube is heated to a temperature T, which is equal to T naught plus delta T, let's suppose the volume of a cube changes to V, which is equal to delta V plus V naught. So this final volume will be L into H into W, where L is the final length of cube, H is the final height of a cube, and W is the final width of a cube. So I mark it as equation number 11. So here is a diagram in which this is the initial condition of a cube, that its length is L naught, height is H naught, and width is W naught, and this cube is at temperature T naught. So when we heat it to temperature T, let's suppose that its length increases to L, height increases to H, and width increases to W. Now, so as we know that volume expansion is actually a three-dimensional linear expansion. So using the final expression we derived in linear expansion for the final length of a cube, final length of a rod, I can say that final length of a cube will be L naught 1 plus alpha delta T, or final width of a cube is equal to W naught 1 plus alpha delta T, and final height of a cube is equal to H naught 1 plus alpha delta T. Now what we do, we just put the value of L, W and H in equation number 11. Equation 11 becomes V is equals to delta V plus V naught is equal to L naught 1 plus alpha delta T into W naught 1 plus alpha delta T into H naught 1 plus alpha delta T. Or we can say that delta V plus V naught is equal to L naught into W naught into H naught into 1 plus alpha delta T to the power 3. This L naught, W naught, H naught is the original volume of a cube. So equation changes to delta V plus V naught is equals to V naught 1 plus alpha delta T to the power 3. I mark it as equation number 12. Now I expand 1 plus alpha delta T to the power 3 using binomial expansion, which says that A plus B to the power n is equal to A to the power n plus n into A to the power n minus 1 into B upon 1 factorial plus n into n minus 1 A to the power n minus 2 B square upon 2 factorial plus up to last term, which is B to the power n. So in this expression, A is 1, B is alpha delta T, and n is 3. So 1 plus alpha delta T to the power 3 is equal to 1 to the power 3 plus 3 into 1 to the power 3 minus 1 alpha delta T upon 1 factorial plus 3 into 3 minus 1 into 1 to the power 3 minus 2 alpha delta T to the power 2 upon 2 factorial plus alpha delta T to the power 3. Or we can say that 1 plus alpha delta T to the power 3 is 1 to the power 3 is 1, then 1 to the power 3 minus 1 is 1 to the power 2, which is equal to 1. 3 into 1 is 1, 3 into 1 is 3, and then alpha delta T 1 factorial is 1. So the term in this expression is equal to 3 alpha delta T. Now 3 minus 1 is 2, and 1 to the power 3 minus 2 is equal to 1 to the power 1, which is equal to 1. Alpha delta T square, and 2 factorial means 2 into 1. And the last term in this expression is alpha delta T to the power 3. So this 2 and 2 will cancel. The equation changes to 1 plus alpha delta T to the power 3 is equal to 1 plus 3 alpha delta T plus 3 alpha delta T to the power 2 plus 3 alpha delta T to the power 3. So in this expression, we know that this alpha is the coefficient of linear expansion, and it is of the order of 10 raised to the power minus 5. So if we square it, it will become 10 raised to the power minus 10, and if we cube it, it will become 10 raised to the power minus 15. So what we do, we neglect alpha delta T square and alpha delta T cube. The equation reduces to 1 plus alpha delta T to the power 3 is equal to 1 plus 3 alpha delta T. What we do, we put the value of 1 plus alpha delta T to the power 3 in equation Equation 12 changes to delta V plus V naught is equal to V naught into 1 plus 3 alpha delta T. So multiply V naught by this bracket. Delta V plus V naught is equal to V naught plus 3 V naught alpha delta T. This V naught will cancel, and delta V is equal to 3 V naught alpha delta T. Or delta V is equal to, we know that delta V is equal to V naught beta delta T. Then V naught beta delta T is equal to 3 V naught alpha delta T. Delta T cancel, V naught cancel, beta is equals to 3 alpha. So from this expression we can say that coefficient of volume expansion is thrice times the coefficient of linear expansion. Okay, now I will drive the relationship between coefficient of linear expansion and area expansion, that is gamma is equals to 2 alpha. So for that I consider a rectangular plate of dimension L naught and W naught. The original area of the plate is A naught and it is at temperature T naught, where A naught is equal to L naught into W naught. I mark it as equation number 13. If the plate is heated to a certain temperature T, which is equal to T naught plus delta T, the area of a plate changes to A, which is equal to A naught plus delta A, where delta A is the change in area and A naught is the original area. The final area of a plate is equal to L into W. I mark it as equation number 14. So in this diagram, this portion that is drawn by a dotted line shows the original area, which is equal to L naught into W naught. And because of the rise of the temperature of the plate, the portion that is red in color shows the change in area of the plate. Okay, now we know that area expansion is actually a two-dimensional linear expansion. So we can say that the final length of a plate is equal to L naught into 1 plus alpha delta T, and final width of a plate is equal to W naught into 1 plus alpha delta T. So what we do, we put the value of L and W in equation 14. Equation 14 will become A is equal to delta A plus A naught into L naught is equal to L naught into 1 plus alpha delta T into W naught into 1 plus alpha delta T. Or delta A plus A naught is equal to L naught into W naught into 1 plus alpha delta T to the power 2. Where L naught into W naught is A naught, initial area of a plate. So delta A plus A naught is equal to A naught into 1 plus alpha delta T to the power 2. I mark it as equation number 15. We try to expand the value of 1 plus alpha delta T to the power 2 using the formula that is A plus B to the power 2 is equal to A to the power 2 plus 2 AB plus B to the power 2. So in this expression, A is 1, B is alpha delta T. So 1 plus alpha delta T to the power 2 is equal to 1 to the power 2 plus 2 alpha delta T plus alpha delta T to the power 2. And now in this expression, again we know that alpha is the coefficient of linear expansion, which is of the order of 10 raised to the power minus 5. So if we square it, it will become 10 raised to the power minus 10. So what we do, we neglect the value of alpha delta T to the power 2. So 1 plus alpha delta T to the power 2 is equal to 1 plus 2 alpha delta T. Now what we do, we put the value of 1 plus alpha delta T to the power 2 in equation number. Or delta A plus A naught is equal to A naught into 1 plus 2 alpha delta T. Multiply A naught by this bracket. Delta A plus A naught is equal to A naught plus 2 A naught alpha delta T. This A naught will cancel. Delta A is equal to 2 A naught alpha delta T. Now we all know that delta A is equal to A naught gamma delta T. A naught gamma delta T is equal to 2 A naught alpha delta T. So this delta T, delta T will cancel, A naught will cancel, and gamma is equal to 2 alpha. So from this expression we can say that coefficient of area expansion is twice times the coefficient of linear expansion. So now in numericals, if you have a disk or a plate, then try to solve it using area expansion, because it is a two-dimensional expansion. Don't apply the formula we derived in volume expansion or linear expansion. Okay, at the end I will explain bimetallic thermostat. First of all, we need to understand what is thermostat. Thermostats are well-known devices commonly used for maintaining required temperature. These devices are physical example of thermal expansion. So bimetallic thermostat is actually a strip, consists of two strips of different metals which expand at different rates as they are heated. So usually we have steel and copper, or in some cases copper is replaced by brass. So due to the different amount of expansion, the strip bends. So here is a diagram in which we have metal having large value of linear expansion and metal having low value of linear expansion, and it is at normal temperature. So when we heat it, due to the different value of linear coefficient of linear expansion, the amount of expansion in two strips is different, due to which the strip bends. So bimetallic thermostats or bimetallic strips work as an electric contact breaker in our electric heating circuit. The one end of the thermostat is fixed and the other end is attached with the pointer. So here is a bimetallic strip whose one end is fixed and the other end is free to move. When the temperature of this strip is increased, the strip bends and the circuit is broken. So we can say that bimetallic strip is used as an electric contact breaker, or a bimetallic strip is used to convert a temperature change into mechanical displacement. So to sum up this lecture, I explain what is thermal expansion, then the difference between thermal expansion of solids and fluid, and after that the types of thermal expansion of solids. Then I derive the relationship between coefficient of volume expansion and coefficient of linear expansion, and after that I derive the relationship between coefficient of area expansion and coefficient of linear expansion, and in the last I discuss bimetallic strip. So I end this lecture by these words, that is, failure is the opportunity to begin again more intelligently. So thank you. If you have any question, feel free to ask. I try my best to answer them. Take care. God bless you.